Okay, we're going to go over section 5.3 from the textbook, which covers independence, conditional probabilities, and tree diagrams. So we're still using the same data. So this was our two-way table. And remember, the first thing you always want to do is calculate the sum of your rows, sum of your columns, and have it. And here we want to find what is the probability of yes taco tongue or yes to evil eyebrow. And we know that we do that by finding probability of the first thing plus probability of the second minus the probability of the and category. So this is where they overlap. That was 20 out of 30, 18 out of 30 minus 15 over 30, which is the overlap. So we got 23 divided by 30. And you could, of course, find the decimal value. Now here's where we introduce conditional probabilities. This is given that the person selected is a yes for evil eyebrow. That means that is your denominator, or the probability of this is your denominator. In this case, it is 18. What is the probability that they are a yes taco tongue? So we're only looking at this column of data. So given that they have an evil eyebrow, that's 18. How many of those also have a taco tongue? That's 15. So 15 divided by 18 gives us 0.833 as a percentage. There we go. And we write that as the probability of having yes taco tongue given that straight up and down line means given that we have this condition, which was yes for evil eyebrow. Here's another one. Given that the person selected is a no to evil eyebrow, so again, we're only looking at this category, the ones with no for evil eyebrow, what is the probability that they are a yes to taco tongue? So that's 5 out of 12, or 0.4166 repeating. And again, we would write that as the probability of yes to taco tongue, given that they are no to evil eyebrow. Now, two events are defined as being independent if knowing whether or not one event occurred does not change the probability of the other event occurring. So if I didn't know whether or not they had evil eyebrow, do I still get the same probability of having a taco tongue? And no, because knowing that they could do evil eyebrow tells us they have a much higher probability of having taco tongue compared to not being able to do evil eyebrow and doing taco tongue. So if these two probabilities were the same, then we would say that yes to taco tongue and yes to evil eyebrow are independent. But in this case, it was no. Okay, let's take a look at the backside. So we're going to do quite a few calculations here. And I've got class worth of data here, classes worth of data. This was from all seniors at a different high school, not here. And probability of getting yes to taco tongue, it's 480 out of 600. Yes to taco tongue, given that it was yes to evil eyebrow, so that's out of 200 through 180. Probability yes to taco tongue, so out of 400, given that there was no evil eyebrow, so no evil eyebrow was 400. Out of those, 300 could do taco tongue. So are these two things independent? Again, if they were independent, all three of these probabilities would be the same. They're not. So they are not independent. So now what we're going to do is say that we know that the probability of a taco tongue is 80%. Could we fill in this table? Still out of 600. But could we fill it in with the values we should have had? So again, forget those ones up here. We're throwing that out. So if we're assuming it's 80% is for taco tongue, that means 20% is not a taco tongue. So I'm going to take my column totals. So yes for evil eyebrow, and what is 80% of 200? So 200 times 0.8 gives us 160 people. Same thing for no to taco tongue. That percentage is 20%. So 20% times 200 gives me 40. So for evil eyebrows, those would be the numbers I have given. And for no for evil eyebrows, again, I'm going to take the column total of 400. And since we're saying if they were independent, 80% of these 400 should be able to do taco tongue. So 400 times 0.8 gives me 320. Likewise, 20% of these 400 should not be able to do taco tongue. And we can double check our numbers now, make sure they add up. So 160 plus 320 is 480. 40 plus 80 is 120. So this is what the table would look like if the events of taco tongue and evil eyebrow were independent. And so now using this table, we're going to fill in this chart. So the probability of having yes to a taco tongue is 80%. So 480 out of 600. The probability of having yes to taco tongue given that you have an evil eyebrow, so evil eyebrow is 200, and 160 of those have taco tongue. So again, 80%. And the converse of this, so yes to taco tongue given that they do not have evil eyebrow. So this column, there's 400, 320 can do taco tongue. So again, that gives us 0.8 or 80%. So what we should notice here is that all the answers up here, when they were not independent, all those percentages are different. Down here, if they were independent, we get the same percentages. The probabilities are all the same. So if we wanted to generalize this, two events, A and B, so in our case it was taco tongue and evil eyebrow, they are independent if the probability of the first event equals the probability of the first event given the second event, which also equals the probability of the first event given the complement of the second event. So that's what all three of these are. So to prove independence, you have to have these values. You have to know that they equal each other. Then you can say the two events are independent. If we wanted to summarize that, the two things we should know out of here is that our conditional probability, we write that as the probability of A given that B. And the way we would find that value is that in the numerator, we put the probability of getting A and B. So from a two-way table, a Venn diagram, a word problem, we would find that probability divided by the probability of event B occurring. So that would be how we'd find that probability. And independent, things are independent when knowing one event has occurred or has not occurred does not affect the probability of the second event. So again, this is our equation. So if the probability of event A occurring is equal to the probability of event A occurring given that B has occurred, which is also equal to the probability of event A occurring given the complement of B has occurred, or sometimes you like to think of it as not B, then we say A and B are independent. And down here we've got a couple of problems. These are in the book also, I believe, but what we're looking at is mothers were surveyed in 1976, 94, and 14. And we're looking at this particular row where they have four or more children. We're calling that C. So these letters were just how we are designating them. This is probability of C given S. So in words, that means given that the mother was surveyed in 1976, there is a 40% probability that she has four or more children. So the probability that she was surveyed in 1976 is 100. The C value is out of this column, 40 of them had four or more children. This next one is given that the chosen mother was not surveyed, so that's the complement of 1976, what is the probability that she has four or more children? So given that she was not surveyed in 1976, so that means she was in 94 or 2014. So we need to write both those values down. So there's the 100s. Out of these two columns, how many had four or more children? So 13 plus 13. That's where these two values come from. So that gives us 26 over 200, or 0.13. So that is the probability that a mother who was not surveyed in 1976 has four or more children. And finally, are the events surveyed in 1976 and four or more children independent? If they were independent, these two values would be the same. These two, and they are not the same. Because we know if a mother was surveyed in 1976, there's a higher probability that she has four or more children than if she was surveyed in something other than 1976. So our probability of four or more children given that she was surveyed in 1976 does not equal the probability that she has four or more children given that she was surveyed in the complement of 1976. It also does not equal the probability of having four or more children, because the probability of having four or more children is 66 divided by 300, which was 0.22. So all three of these probabilities are different from each other. Okay, let's take a look at the second half of these notes. This is going to be our ace game. And actually, I'm using the different problems than we had in class. But, well, it's the same problems, but just different numbers. So in this game, or this event, if you had 2 aces and 3 kings, and you randomly were drawing cards. So here's where I'm just showing what I drew for the first card, and then without replacing it, draw a second card. If we get 2 aces or 2 kings, you win. So I've gone through and done it 10 times, and I found that my probability here, 3 different times out of 10, I got winners. So that was 0.3%, or 0.3 probability, or 30%. Now, if we went through and did this lots and lots of times, which is what I did in a simulation, so I had 116 out of 300, that was a 0.387%. And just remembering from our previous class, which one should be closer to our theoretical probability? It should be this one by the law of large numbers. But we're going to go ahead and calculate what that probability should be. So we are creating a tree diagram to show this situation. And what we're going to do is we start off, we're playing this game, and we have 2 possibilities. I draw an ace or I don't draw an ace. The probability of drawing an ace on the first card is 2 out of 5 because there was 5 cards. And the probability of not drawing an ace so that I get a king is 3 out of 5 because there was 3 cards that were kings. Let's look at the ace scenario first. So if I drew an ace the first time, that meant there was 4 cards left over. So out of those 4 cards, I have 3 kings and 1 ace. So I'm going to draw another card. The probability of getting the second card to be an ace is 1 out of 4. So there's my 1/4. My probability of drawing the second card being a king is 3 out of 4. And notice that 1/4 and 3/4 has to add up to 1 because there's only 2 possibilities, again, ace or a king. Likewise, if the first time I drew a king, so here's my cards, the second card, the probability of getting an ace, I have 2 out of 4 chances of getting an ace and 2 out of 4 chances of getting a king. So once I have all these probabilities in my table, to find the probability of the first card being an ace and the second card is an ace, that probability I get by multiplying the probabilities along this branch. So the first probability was 2/5 times 1/4 gives me 2 over 20. The probability that the first card was an ace and the second card was a king, again, multiply the probabilities as you go along the branches here. So 2/5 times 3/4. Down here, this value represents the probability of drawing the first card as a king and the second card as an ace. So multiply 3/5 times 2/4. And this final one is the first card is a king and the second is a king. So 3/5 times 2/4, and we get 6 over 20. And one thing to notice here, if we were to add all of these probabilities together, because these are the only probabilities that exist, there's no other order that we can do them in, or any different cards we could get. 2 over 20 plus 6 over 20 plus 6 over 20 plus 6 over 20 adds up to 1. And our probabilities always have to add up to 1 to be a good probability model. Right here, the 2 possible choices add up to 1. And right here, the 2 possible choices add up to 1. In the very beginning, we only had 2 choices, and again, they add up to 1. So at each decision point, your probabilities have to add up to 1 as well. And so again, if we're going to look at how we write this, this is probability of getting the first card as an ace. This probability right here is the probability of getting the second card as an ace, given that the first card was an ace. And here's my little formula now. This was the probability of getting first card as an ace and the second card as an ace. That formula is the probability of getting the first card as an ace times the probability of getting the second card as an ace, given that the first card was an ace. And I could write that out for each one of them, but it would be too messy on here. Let's take a look. What is the theoretical probability of winning the game? Well, to win, we had to have two aces or two kings. So the probability of this was 2 over 20. Probability of getting two kings was 6 over 20. And I add those together. So I get 8 over 20, or 0.4 is the probability. Now we want to know, what is the probability that the first card was a king, given that the person won the game? So given that they won, well, that probability we just calculated here. That is a 0.4 probability. And what is out of these ones that won, what was the probability that the first card was a king? Well, that had to be this scenario, because up here is two aces. So this one, the probability that the first card was a king and the second card was a king was 6 out of 20. So 6 divided by 20 divided by 8 divided by 20 gives us a 0.75 probability. So again, that's a 0.75 probability that the first card was a king, given that the person won. Okay, let's take a look at the learnings that we should have had. So 3 different things here. First was the general multiplication rule, and that is that if you're looking for the probability of A and B, we can find that by multiplying the probability of event A occurring times the probability of event B, given that probability A happened. Remember, this is a conditional probability right here. If A and B are independent, remember that if they're independent, they have the same probability of things happening, then the probability of event B happening given A is the same as probability B. So that I can substitute into here, and I would have the probability of A and B is the probability of event A times the probability of B. So this is true when they are independent, when events A and B are independent. And we also learned about a tree diagram. And a tree diagram simply takes your two choices, probability of event A and the probability of the complement of A, so not A. So that's going to be some value. This probability plus this probability have to add up to 1. We then, given that we had event A, we then can see what's the probability of getting event B or event C. And again, this probability is what is the probability of event B given that A happened. This is the probability of event C given that event A occurred. And down here we can do the same. So the ending values over here for your probabilities is we would multiply these probabilities together. If I wanted to find this one right here, probability of not A and B, I would take this probability multiplied by this probability, and I would have this one. The sum of all of these probabilities have to add up to 1. And the last thing, and this is just more English language, is if we are asked for what is the probability of at least one thing happening, the only way that not the only way, but the easiest way to solve for this is look at the cases where that doesn't happen. The only way you don't meet this criteria is for it to happen, or for none of them to happen. So probability of at least one event occurring, you just subtract the probability of no events happening from 1. And that will be the probability of at least one happening. So for instance, well, there's some examples down here that we could take a look at. But here's a tree diagram. Again, this was based on what way each state voted in the 2016 election, and then whether that state was in the continental U.S. or in the non-continental U.S. So that meant it was Alaska or Hawaii. And we got all these different percentages by multiplying as you go down here. If we select 4 states at random with replacement, what is the probability that at least one of the states is in the continental U.S. and went Republican? So the probability that they are in the continental U.S. and went Republican, we want to look at what's the probability that none of them are. So if this is the probability of being in the continental U.S. and being Republican, the probability of not would be 1 minus this amount, so 0.42. And since we want to do it 4 times, we would have to have 0.42 times 0.42 times 0.42 times 0.42 and subtract that from 1. So take a look at this, look over and read section 5.3, and let me know if you have any questions.